All right. So what we're going to be doing today is we're going to kind of continue working with these word problems, but we're going to learn how to sort of rewrite these functions. So like the functions that we just wrote for the bell ringer, we're going to learn how to rewrite them based on what type of growth you're looking for. So that sounds kind of vague right now, but let's get into it. You'll understand more as we do it. Can I have a volunteer please read what is going on here? Who can start us off?
Monthly growth versus yearly growth. Consider the two babies below, both which represent the population in the town of Florida, which started with 1,000 residents. A table A represents a population every month. Table B represents a population of the same town every year. Calculate the monthly rate of growth and the yearly rate of growth. What do you notice?
All right. So thank you, Raymond. So basically, both tables represent the same exact town. It's just that one of them is showing us what happens every month, and the other one is showing us what happens every year. So I want to start off just by calculating the rate of growth, the percent rate. How do I do that? Someone remind me?
Subtraction?
Careful, not subtraction, because we're talking about
No, division.
Division. Good. Since we have exponential functions, we're talking about exponential functions right now. We go from where to where? Bottom up or top down?
Bottom up.
Bottom up, and we're just going to divide, divide, divide. So calculators out, and in fact, calculators out for the whole class today. We will use them pretty frequently, so you may keep them out. And we're just going to divide. So 1,255 divided by 1,231. I get 1.019. And we're just going to keep going a couple times until you start noticing a pattern. So 1,231 divided by 1,208, I get 1.019 again. I'm just going to do it maybe 2 more times because you always just want to double check that you keep getting the same number. Just want to make sure. Okay, we got 1.0185. And then the last time, 1186 divided by 1163, I get 1.019. So they all round to the same number. Even though this one is 185, how do I know that that's going to round to the same value?
Because since the 5, I remember that term or quote that you used to say, 5 something for lower.
Yeah, how did there was a little rhyme that helps you remember. So 5 or more, raise the score. 4 or less, let it rest. So since I have a 5 and the quote says, okay, 5 or more, raise the score, I can round my 8 up to a 9. So long story short, if you divide, and if you go all the way to the top, you'll still notice that you get the same exact value. You still get 1.019. So that number is my rate. My rate of growth is 1.019. But actually, this is my monthly rate of growth. Okay, because whatever number you get, whatever number keeps showing up on your calculator, that's your rate of growth. Okay, now, if that's my rate of growth, what is my percent of growth?
Do we have to subtract?
Think about how we do this when if I were to write a function, how would I figure out the percentage?
You
Is the
could
percent
subtract.
What was that, Lauren?
You could subtract.
Okay, so subtract what?
1 minus, was it 1.01919?
Okay, but is this remember, are we growing or decaying?
Oh, growing.
Growing. So remember that that percentage, whatever, if you're growing or decaying, the percentage is the number that was either added to one or subtracted from one. So in this case, since it's growth, what number was added to one?
Number was added to what number?
What was
19. 0.19.
0.019. Okay, so 0.019 as a decimal, what is that?
As a decimal?
As a percentage, sorry.
1.9.
1.9, you got it. 1.9. Because, okay, 1.019, that's 1 plus 0.019. So 0.019 as a percentage is 1.9%. And that's what you always want to think about. What number was added to 1? Or if it's decay, what number was taken from 1? And you got to kind of work your way backwards to figure out the percentage. Because there's a difference. The growth, the rate of growth versus the percentage of growth, those are two different things. You got to be very careful. So any questions on how I got my rate of growth? Any questions on how I got my percentage of growth? Okay. So now I want you guys to go do the same exact thing with table B. Find the rate of growth, and then from that, figure out what was the percentage of growth. And we're just going to compare and see what's different and talk about it.
We could do 4 columns only.
Yeah, you do not need to go all the way up because I already told you that these are exponential. So the only time that you have to go all the way up is if you're trying to see whether it is exponential or not. But I'm already telling you these are exponential. So really you just have to do it a few times until you see the same number showing up. Okay, just a couple more minutes, couple more seconds, I mean. And 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. So when you divide, what number keeps popping up on your calculator?
1.2577.
So the first one, 1.2555 is what I got. But you might see it changes a little bit each time. So the second two, I get 9. Oh wait, no, the first, sorry, that was wrong. 15266 divided by 12,164. Yeah, 1.255. 12,164 divided by 9,692. 1.255. Okay, so we keep going that way, and you just keep going and going until you get the same exact number in your calculator. And if you keep going, you'll pretty much keep getting the same thing, 1.255. Now, we always want to round that number to the nearest hundredths place at least. So actually, no, let's just keep it as 1.255, and I'll show you why in just a moment. But my rate of growth is 1.255. 1.255. Any questions on how I got that? Well, if that's my rate of growth, then what is my percentage of growth?
0.255.
0.255. And what's 0.255 as a percentage?
25.5%.
25.5%. Good. 25.5%. Okay. Any questions on how I got any of those numbers? Make sure that you understand. If you do not understand, you need to be asking me questions. Okay, but let's actually talk about it now. So on the one hand, on a monthly basis, the population is growing by 1.9%, but on a yearly basis, the population is growing by 25.5%. Now, why do we think that's happening? Why?
For which table or both?
Why do we think there's such a big difference? It's the same exact town, right? Same exact town, but on a monthly basis, it's only growing by 1.9%, but on a yearly basis, it's going by 25.5%.
Because there's less time for babies to be born
Mm,
in a month and a year.
good. So that's a really good point. And because let's actually think about it. How do populations grow? Some more people join from outside, but at the same time, the people who live there have babies, right? And the babies have babies, and the babies of the babies have babies, and that's how you get growth. So that's a really good point, Raymond. Yeah. If you wait a whole year, you give it more time for people to come in or for people to be born. Anything else? Any other questions or try to explain why that's happening? I see a couple questions about the percentage, but I'll go over that in just a moment. Okay, so let me explain this percentage situation again, because I know a couple people are confused. Okay, so if the rate of growth is 1.019, really what that's telling me is that it's 1 plus 0.19. 0.0, sorry, 0.19. And 0.019 as a percentage is 1.9%. And that's the same exact thing goes for the other one. If you're trying to figure out what the percentage of growth is, you have to figure out what number was added to 1. So this is 1 plus 0.255. And then 0.255 as a percentage is 25.5%. So for any table, anytime you have to calculate that, that's exactly how you do it. You figure out what was added to 1, and that decimal becomes a percentage. So any other questions on how you get that percentage? Okay, cool. So this is something that's very interesting. And what happens with exponential growth is that when you think about it on a smaller time scale, so monthly versus yearly, when you kind of look at it on a smaller scale, the rate of growth gets smaller. When you think about it on a longer scale, the rate of growth gets much bigger. So what happens is sometimes when you have a function, you might want to figure out, instead of the yearly amount, you want to figure out the monthly amount, depending on what you're trying to calculate. So before we get into that, does anyone have any final questions on this page? Okay. So same exact tables. Let me just rewrite. Matter of fact, I'll copy this. Hold on. No, did not mean to do that. There we go. Copy and paste. Okay. Same exact tables, but now we're doing something else. Now we're going to write a function that represents table A, and we're going to write a function that represents table B. So I know the percent of growth. What else do I need to know in order to write my functions?
The y-intercept?
Good. Good. Just like we did in the bell ringer, okay? Same exact thing. Instead of a word problem, I have a table, but we're doing the same thing. We figure out what the percent of growth is, and we also figure out the y-intercept. Well, the y-intercept is always your starting amount. So what is the y-intercept for both of these?
For table A, it's 1,000. Oh, okay, it's 1,000 for both of them. I'm sorry.
No worries. It's 1,000 for both of them because remember, they both represent the same town. So that makes sense, right? We want it to be the same. Okay, so I have my percent, I have my y-intercept. Now I can write my function. And let's call this one P of M, because it's going to be months. So P of M, what do I write first?
1,000.
1,000. There's my parentheses, and I know that I'm doing 1 plus 0.019 to the power of M. But like I always do, like I always say, we got to just simplify what's on the inside. So I end up with P of M equals 1,000 times 1.019 to the power of M. And M represents months. And then I can do the same exact thing with table B. This time though, I'm going to call this P of Y, just because it represents years rather than months. So that's the only reason. So P of Y is going to be 1,000 times 1 plus 0.255 to the power of Y. And when I just simplify, I get P of Y equals 1,000 times 1.255 to the power of Y. Okay, this is the same thing we did in the bell ringer, same exact thing, just that I started from a table rather than a word problem. But it's the same two things go into those parentheses. So now it says, let's read ahead. So now it says, say you want to know the population in the town after 25 years. What would you plug into function A and what would you plug into function B? And the question is, would you get the same answer? So let's kind of break that down. If I want to know the population after 25 years, what would I plug into? Actually, no, let me start with function B. What would you plug into function B?
25.
Yeah, 25. Because we're trying to figure out the population after 25 years, and the letter Y already represents years. So I'd write 1,000 times 1.255 to the power of 25. So that would be function B, but what would you plug into function A?
Plug into function A.
Mm-hmm.
25. No, it can't be 25 too, right?
Right. What is, if you look at function A, what does the variable represent?
Months.
Months. It's months.
Do
So
we have to divide 25 by 12?
Okay. So how many months are 25 years?
2.08.
Months?
Month can't be calculated with decimals, right?
No. So let's rethink that. How do I figure this out? How do I figure this out? If I know it's 25 years, how do I figure out the number of months?
You divide.
I divide by what?
By 12 divided by 25.
Okay, what's 12 divided by 25?
0.48.
Does that make sense?
No.
No.
No, so maybe I'm not dividing. Maybe what am I doing instead?
Subtracting? Wait.
No.
Multiplying.
Multiplying. Yeah. How many years? Okay, how many months go into a year? 12, right? So if I've got 25 years, I have to do 12 times 25. So go ahead and do that in your calculator. What do you get?
300.
There we go. 300. So it's 300 months. So into function A, I have to plug in 300 because I have to use, this is in terms of months, not in terms of years. So I'm plugging in 300. It's a big number. Now, what do you guys think? I haven't done the math yet. Do you think we'll end up with the same answer or a different answer?
Probably the same.
Yeah, thought so too.
Yeah, right? Because it's representing the same town. So it shouldn't be any different. So let's go ahead and check. So in your calculators, I'm going to show this one more time to make sure we all know how to do it. I'll start with function A. So we're doing 1.019 to the power of 300, and then take that number and multiply it by 1,000. So here we go. So it's 1.019. Which one's my power to, what button do I use to put it to the power of 300?
X to the power of Y. It's
Good.
in the middle. Yeah.
Good. X to the power of Y, hit 300, hit enter. Then I take that number, I'm not going to erase it, I'm just going to multiply it by 1,000. And here's my answer. I got 283,300, and I'll round it to the nearest person because we're not going to have a decimal of a person. So to the nearest whole person, should I keep it as 305 or should I round it up to 306?
306.
Good. So I get P of 300 is 283,306. Well, now I'm just going to do the same exact thing with my other function, but this time it's different numbers. So I'm doing 1.255 to the power of 25, and then multiply that times 1,000. So 1.255 to the power of 25, multiply that times 1,000. And I got 292,477 or 78?
77.
Stays at 7 or rounds up to 8?
To 8.
8.
Good, up to 8.
Wait, where
Okay,
up from the 9 or the 6?
because you always look at the next number over. So if I'm rounding it to the nearest whole number, I look at the ones place, the 7. The next number is a 9, so my 7 goes up to 8. So it's 478.
Oh, I thought we were rounding on the other side on the
Oh, I got you.
I saw the 0, so I thought it was supposed to say this.
That's okay. Okay, so we got a slightly different number, 292,478. That's okay though. That's okay. They're slightly different, but at the end of the day, it's because we're trying to figure out something way in the future. 25 years, that's a very long time. So the numbers, even though they're not exactly the same, they get us, it's a prediction, right? We're looking into the future, it's a prediction. And both of these functions get me pretty close. They're not too far away. They're not too far away from each other. So they get me pretty close. And I know that in 25 years, the population is going to be like right under 300,000 people. Okay. So let's actually think about what we did. We had two different functions, right? They have different numbers in them. And they represent the same town, the same situation. And the way that this works is that the rate, which rate is smaller? The monthly rate or the yearly rate?
Monthly.
The month.
Monthly. Good. The monthly rate is smaller, so we had to plug in a much bigger number, right? We plugged in 300. The yearly rate is much larger, but we were able to plug in a much smaller number. So which of these, if I'm asking you, okay, tell me the population of the town after 50 years, which of these two functions is going to be better to use, A or B?
I mean B.
Right, B is a lot easier because I can just plug in 50. I don't have to convert it into months. I don't need to do all that. I can just plug in the number straight up. But if I ask you, what is the population of the town after 15 months, which function is easier to use, A or B?
A.
A, right? Because if I'm asking you to tell me the months, you can just plug that straight into table A or function A. So both functions are representing the same situation, but one can be easier to use than the other depending on the question. So here's one last, same table, same everything. One last question. If you want to know the population after 18 months, which function is going to be better? What did we say?
A.
Good. So function A would be easier to use because you can just plug in the 18. So any questions on so far? That's basically it for this table, for this situation. Any questions on this page? Okay. Well, let's look at a slightly different, well, we're still kind of talking about the same numbers, but slightly different situation. Can I have a volunteer read our new situation, please?
Jeffrey's gonna read.
Okay.
All right,
Jeffrey,
thank you.
come on.
All right, thank you.
Go ahead.
On September.
Come on.
Oh, I just read. All right.
Let's go. What's going on?
Ms. Lopez, put a Z in the grade book for Jeffrey for today. You don't want to read.
Jeffrey, let's go. Come on. It's not that hard. Jeffrey, I'm asking you nicely now. It's your last chance. Guillermo, go ahead.
On September 8th, 2015, the price of gold reached $1,000 per ounce. Over the next year, the price of an ounce of the gold was molded by Y equals 100, 1.255, where T is years after September.
Perfect. All right, thank you. So we already know this time we have a function. Now we're going to explain what's going on in it. So this is something that we should already know by now, but what does the 1,000 represent?
Starting amount.
The starting.
Good. Starting value, starting amount. So we know that that's 1,000 what? What's the units?
Per ounce.
Yeah, but 1,000 what?
Ounces?
Dollar.
Dollars.
Oh, dollars. Oh, I'm sorry.
That's okay. $1,000. Okay, what does 1.255 represent? What's 1.255?
That's the amount after you add the 1.
So remember, there's two different things. There's the percent, and then there's this. This is the other thing. What's this called? Starts with an R. You're overthinking it. You guys are overthinking it. It's the amount that we multiply by each time. What is that called?
The growth rate.
Growth rate. Thank you. Rate of growth. That's all it is. It's the rate of growth. That's it. We already, you guys know that. You're overthinking it because there's the rate of growth, but then there's the percent. So that's the next question. What is the percent of increase?
$25.5.
You got it. 25.5%. How'd you get that?
Subtract the 1 and then turn it into a decimal.
Turn it into
Multiply it to 100.
Good. So turn it into a percent. Exactly. So that's the same thing we were doing before. So this is the same as 1 plus 0.255, and 0.255 as a percentage is 25.5%. And then finally, what does the T represent? Good. I see it in the chat.
Years.
Bianca's got it. Good. Years. So very important. This is years after September. And you always want to know what that number is. Is it years? Is it months? Is it weeks, days, hours? Because it's going to matter what you plug in. Because now, let's say that you want to know the price of gold after 1 month. If you want to know the price of gold after 1 month, what are you going to have to plug into the function?
What was the question again?
Number 5, suppose you want to know what the price of gold will be after 1 month. What number would you have to plug into the function?
1? No.
Because the T is representing years, right?
Yes.
But I want to know what it's going to be after 1 month.
Do you write a decimal?
So you're on the right track. You're on the right track. It's not going to be a decimal though. I want to keep things as a fraction. So it's kind of weird to think about, isn't it? But let me show you something that might help. So we know that 1 year is how many months?
12 months.
12 months. 1 year is 12 months, right? So if I want to know how many years is 1 month, so it's kind of like if you want to go the other way. Okay, if you want to go the other way and figure out how many years is 1 month, well, you're just going to do the opposite. Instead of multiplying by 12, I'm going to have to divide by 12. So 1 month is how much out of a year?
0.08.
How'd you get 0.08?
I divided 1 divided by 12.
You did 1 divided by 12. Yeah, so we're going to keep it as a fraction though. 1 out of 12. Because think about it. A year is 12 months, right? So let me actually break this down. Hold on. Let me do this way. So 1 year is 12 months. So 12 out of 12. 12 out of 12 is 1 year, right? Because 1 whole, 12 out of 12 is 1. But if I only have 1 out of 12, that's 1 month. So 12 out of 12 is 1 year. 1 out of 12 is 1 month. Because you take 1 month out of 12 total months. It's kind of hard to think about, but just remember it this way. I'm just going to keep writing it this way. So 1 out of 12 years is 1 month. That's the relationship. So I'm going to just kind of circle that, highlight it, write it in your notebook. So in order to figure out what the value of gold is going to be after 1 month, well, you're just going to plug in 1/12 into your function. So you would plug in 1/12. Kind of weird to think about it. Does anybody want me to explain it a different way? Okay. Cool. Okay, so this is where it kind of gets interesting because if you're trying to break it down and get into a smaller, like if you're trying to plug in a fraction like this, the function's a little bit harder to work with, right? Does anybody like plugging in a fraction into your calculator is already hard enough as it is. So it kind of makes it a little bit more difficult to use that function if I'm going monthly. If I'm trying to plug in a number of months, it's going to be harder to use that function. So what we're going to do is we're going to rewrite the function. We're going to rewrite it so that you don't have to plug in fractions. I'm going to rewrite it so that I can just plug in whole numbers, and that'll be a lot easier for me to do. So before I do that, last call, any final questions on this? Somebody's asking me, how do you get the decimal? Which decimal? Be more specific. The 0.08. Okay, so when Lauren got 0.08, because she said, okay, 1/12 is 0.08. Did you do that in your head, Lauren, or did you just use your calculator?
I use the calculator.
Okay, yeah, that's what I was thinking, because I would also just use my calculator. It's just 1 divided by 12. If you go on your calculator, 1 divided by 12 is 0.083 repeated. So in this case, it's not that easy to convert it into a decimal because, like I said, if it's a number over 10, over 100, or over 1,000, pretty easy. But when it's something like this, over 12, it's not that easy to do in your head. So she just used her calculator. Okay, so let's get into it. So let's see what this is going to do. So like I said, we're going to rewrite the function so that I can plug in the number of months. So I can figure out the monthly percent increase. Because going back, remember, what is the percentage of increase in this case?
25.5.
25.5%. And that's 25.5% per year. Per year. But if I want to know the percentage per month, that's what we're going to have to change. So we're going to have to change up this function. So the first thing, like we already did, we're going to find the conversion rate. And remember, what we already wrote this down. We said that 1 month is 1/12 of a year. So that's the first thing. You always want to think about what is the conversion rate. If I want to go from yearly rate to monthly rate, first thing is just figure out, okay, how many years go into 1 month? Then we're going to rewrite the function. And look at what it says. It says rewrite the function without changing the function. Okay, that's a little strange, but let me explain what I mean. So I'm just going to start off writing it the same way. So it's y equals 1,000 times 1.255 to the power of t. Haven't changed anything yet. But remember what we said. We're going to plug in 1/12. Okay. So if I want to plug in 1/12, if I want to plug that in, I also want to make sure that I'm not changing the value of the function. So what does that mean? Think about a function. A function is an equation. An equation has a balance. Think of it like a seesaw or like a balancing scale or something like that. It's balanced because it has an equal sign. Well, if I change something on the right side, is the equation going to be in balance anymore? If I add something to the right side of my equation, is it going to be balancing?
No.
No, it's going to be out of balance, right? Well, what did I just do? I just put an exponent in my equation. That's going to throw me off balance. So what I need to do is I'm going to try to push it back into being in balance. So the way to do that, and this is going to be a little odd, but I just want you guys to stick with me for a moment. What I'm going to do is, in order to push myself back into balance, I'm going to undo what I just did. So I'm going to say that one more time. I'm going to undo what I just did. So what's the opposite of dividing by 12?
Multiplying by 12.
Multiplying by 12. So I'm going to put in a 12, a whole number, back into my equation. So this is definitely weird, y'all. I know that this is weird. So don't freak out. Don't be all confused, because trust me, just live in the confusion for a moment. But think about why I did what I just did. I needed to plug in 1/12 in order to know how much you make in 1 month. I needed to do that. But when I did it, my equation went off balance. So in order to push it back into balance, I also had to plug in a 12. Because what actually happens? What actually happens when you multiply, because these are exponents and we got to multiply them, what's 12 times 1/12?
12 times 1/12.
Mm-hmm.
12/12.
12/12. And what's 12/12?
1.
It's 1. So did I actually change anything about the equation at the end?
No.
Not at all. But now, and here's why the reason I did it in the first place is because now, step 3, simplify to find the new percent rate of growth. Now what I can do is I can take what's in here, okay? And I'm going to plug just that into my calculator. So I'm doing 1.255 to the power of 1/12. So let me go back over here. 1.255 to the power of 1/12. What I'm going to do, I'm going to type in 1/12, but I'm going to use my parentheses to do so. So I open my parentheses, 1 over 12. Oops, I did 1 over 2. Hold on, I got to start over. Okay, 1.255 to the power of, parentheses, 1 divided by 12, close those parentheses. And here's my answer, 1.019. So I'm going to do that one more time so everybody can see what I did. So one more time. Remember, I'm doing 1.255 to the power of 1/12. So it's 1.255. Use my power button to the power of. But now the 1/12, I'm just going to close, I'm going to put that in a parentheses so that my calculator doesn't do the wrong thing in the wrong order. So I'm just keeping that fraction inside a pair of parentheses. That's all I'm doing. So I open my parentheses, 1 divided by 12, close my parentheses, and hit equals. So there it is, 1.0191. So I'm going to rewrite this. Y equals 1,000 times 1.0191 to the power of 12t. So here's what's going on here. T is still t. I didn't change what that represents. So t still represents years. So I'm still going to plug in years. However, the number inside of the parentheses is my monthly rate. It used to be the yearly rate. Now it's the monthly rate. And the reason you might want to do that is because, like I said before, if you have the yearly rate, it's hard to tell what's going to happen after 3 months or after 4 months or after 5 months. But when I have the monthly rate, then I can plan ahead and I'm going to know exactly what's going to happen 6 months from now or 4 months from now, or just a number that is less than 1 year. And so what we're going to be doing for the rest of class, we have about 20 minutes left. We're just going to do this over and over again because I know that it's kind of weird and confusing and it might not make a lot of sense to you. Trust me, it didn't make a whole lot of sense to me either when I first had to teach it. Like 2 years ago when I taught this for the first time, I feel bad for my students because I don't think I did a good job of explaining it. So don't worry if it feels a little confusing or different. I just want you guys to practice it a few times, and I promise you, the more you practice it, the more it's going to make sense. So at this time, are there any questions? Any questions? Okay, so we're going to do another example. It's very similar. Can I get a volunteer? Actually, Raymond, you're going to have to read this one because that's your last name.
Henry created a model that represents the population in a rapidly declining city during a particular decade. According to the records, there are 714,000 people living in the city at the start of 1990, and the population had decreased by 25% by the end of the decade.
Perfect. So we're going to start with writing a function. So it says write a function P of D that represents the population in this city D decades after 1990. So what's my starting amount?
714,000.
714,000. My percentage is 25 and it's decreasing. So I start with the percentage. What's 25% as a decimal?
0.20, no, yes, 25.
0.25. And here we go, let's write this function. So P of D equals 714,000. And then am I adding or subtracting?
Subtracting.
So it's 1 minus 0.25 to the power of D. Okay. And now I can just simplify this. So P of D equals 714,000. And what's 1 minus 0.25?
75, 0.75.
0.75 to the power of D. Okay. I'm going to fix this. Okay. Quickly, let's go ahead and answer these questions. So this should already be pretty familiar. What does the 714 represent?
Starting amount.
Starting amount. What does the 0.75 represent?
0.75 represents the growth rate.
Okay, but are we growing?
I mean the decay rate.
Decay rate, good. And then what's the percent decay?
0.25.
And we're going to
5%.
Good. Keep it as a percentage. So 25%. So the decay rate is 0.75, but the percent of decay is 25 because it's the number that was taken from 1 to give me 0.75. What does the D represent?
Years.
Careful.
Decade.
Decades. Good. Okay. Suppose you want to know the not price of gold, my bad. Suppose you want to know the population. What the population will be after 1 year. What would you have to plug into the function?
One over 10.
You got it. You got it. Good job. See, it starts making a little more sense the more you do it. But that's the same thing, kind of similar to what we did with the month and the years. So I know that 1 decade is how many years?
10.
10 years. Right? So going the opposite way, if I want to know how many decades go into 1 year, you just divide. So this is 1 over 10. So if I wanted to know the amount of people in this city after 1 year, I'm going to have to plug in 1 over 10. Does anyone have any questions on that? Okay. So now we're going to do the same exact thing as before. We're going to rewrite the function so that it shows me the yearly percent. Because I know the decades percentage is 25%, but I want to know the yearly percentage. So first thing, we already found the conversion rate. So one year is 1/10 of a decade. I'm going to start with the same function as we had before. So we start with the same function. I already know I'm going to plug in 1 over 10. But when I plug in 1 over 10, what do I have to do to bring it back into balance?
Place a 10 on the outside with D.
You got it. Place a 10 on the outside. So here we go. So I have 714,000 times 0.75 to the power of 1/10. That throws me off balance, so now I have to place a 10 on the outside with the D. Okay, because again, I'm momentarily throwing it off balance and then quickly correcting it to bring it back into balance. And then the last thing is to simplify by calculating 0.75 to the power of 1 over 10. So I'm going to give you guys a moment to just write everything down, and then I'll go and switch over to the calculator so you can see how to do that. Okay, so here we go. So I'm doing 0.75 to the power of 1/10. So I hit my xy to the power of, then I hit my parentheses. I write 1 divided by 10, and I close my parentheses. And is that my answer, or should I hit equals?
Equals.
Hit equals. Don't forget to hit equals. And I got 0.97. I'm going to write 0.972. 0.972. So P of D equals 714,000 times 0.972 to the power of 10D. So what is my yearly percent of growth? Of decay. Sorry.
0.972.
Be careful. That's the rate. What's the percentage?
97.2.
Be careful.
Oh, the percentage. Oh, I'm sorry. Since it's decaying, we have to do 1 minus 0.972. 0.028, which is 2.8%.
You got it. 2.8%. So be careful, Lauren. Don't worry. Everybody, this happens to me all the time. Remember, you're looking for the number that you took away from 1 in order to give you 0.972. So let's go back for a moment. What was the decade percent decay?
Decade percent decay. 75%.
Careful. Remember what I just said? We got to see what was taken from 1.
Oh. $25%.
Good. So per decade, you lose 25%, but each year you only lose 2.8%. So that's kind of similar to what we noticed before, that when you increase the amount of time, the percentage gets much bigger. When you look at a smaller amount of time, the percentage is much smaller. So each decade, you lose 25% of the population, but each year, you only lose 2.8% of the population. How do we feel now? I know it's still a little weird. Do I have any questions? And I promise you guys, this lesson is always, people find it the hardest, but on the test, there's like 2, maybe 3 problems related to this topic. So it's not a huge part of the test, but if you understand it, that's going to help you a lot with answering those questions. So how do we feel? Any questions on this? Like I said, we'll do a few more examples. Okay. Let's do another one. Now I'm going to write fewer things because now that we kind of get into the groove of it, I'm going to just write fewer questions on the side of the board, but let's go ahead. So a function, p equals 50,000 times 1.03 to the power of t, describes the percent increase, p, in the cost of college tuition in the state of Florida each year. Okay. So what is the yearly percent increase in tuition?
Yearly percent. 3%.
Good. How'd you get that again?
Since I looked at the growth rate,
Mm-hmm.
and since it's addition, I just took away the one from the
I know it's a lot of words. You took the one from the decimal.
and then it gave me 0.03, and then 0.03 in percent. It is 3%.
Good. 3%. So the tuition in Florida increases by 3% each year. By the way, what does the 50,000 represent?
Starting amount.
The starting amount. So it's how much it costs to go to college on average. $50,000. It's a lot of money. Okay. And then the T, what does the T represent?
P or T?
T as in Tom.
E. The T each year.
Yeah.
Year. Good. You got it. T is number of years. Okay, cool. We got all that down. Now we're going to transform the function so that it expresses the percent increase in tuition each decade. So what do we expect? Is the percentage going to be much larger or much smaller?
Larger.
Good, because 3% is the percentage each year. So if I go up to decades, I expect that percentage to be a lot larger because I'm going from years to decades now. So let's start off with our conversion rate. 1 decade is how many years?
10 years.
10 years. Okay, so this time I'm going to be plugging in a 10. So I start off with my original function. And since I'm plugging in a 10 on the inside, what should I do to the outside?
Plugging in a 10. No.
How do I throw my equation back into balance? If I'm plugging a 10 on the inside, it's off balance. What do I do now to bring it back?
Plug in a exponent.
And what should that exponent be?
1/10.
1/10, exactly. So whatever you plug into the inside of the parentheses, you just got to do the opposite on the outside to bring it back into balance. Because 10 times 1/10 is just 1. So if I plug in a whole number on the inside, my fraction goes in the outside. If I plug in a fraction on my inside, the whole number goes on the outside. It just depends on which direction you're going. Because in this case, and let me actually go back one slide. Here, I started with decades and I needed to figure out the years. So I went from big to small. But in this case, I'm starting with years. Let me bring this down. I'm starting with years and I'm going up to decades. It's increasing. It's going up. So that's why this time I put the 10 on the inside and the 1/10 on the outside. Kind of confusing. Any questions on that? I know this is strange. And trust me, tomorrow, we're just going to keep working on this. We're staying on the same topic tomorrow so that we have more chances to practice it. So what's my final step?
Simplify inside the parentheses.
Good. So I take this. Let's go to my calculator, 1.03 to the power of 10. This is a little bit easier this time because now I don't need parentheses. I can just go with the 10. So I got 1.344. 1.344. To the power of 1/10 t. So let's talk about it. 1.344 is my yearly rate. So what is my new percent? My yearly percent of increase.
0. The decimal will be 0.
Or my, sorry, not yearly, my decade percent.
Oh. Since it will be 0.344,
Mm-hmm.
it will be 34.4.
34.4%. So going back, 3% is the yearly percent. So this is per year. So each year the tuition increases by 3%, but over time, after each decade, that's a 34.4% increase. So again, the bigger the unit, the bigger the percentage. For years, it's much smaller. For decades, it's much bigger because you're covering a larger amount of time. Okay, I want to pause where we are to just do a quick little pulse check because I know that this is kind of confusing, kind of difficult for a lot of people. So in the react buttons, with the react buttons, give me either a thumbs up, or if you feel a different way, give me a different emoji. Just let me know how you're feeling about this so far. Okay. Allison's got a little bit of a shock face. I totally get it, Allison. If you feel a little shocked, you can do that too. Bianca feels the same way. That's all good. And I saw a couple of thumbs ups. That's also good. Okay. Someone just sent me like the little like weird, I don't know how to describe that face, but the weirded out face. I get it. I get it. I get it. Trust me. This is the one topic where if you don't understand it, like I totally am with you. I got you. Okay. Well, I wanted to do one more. I know that the bell's about to ring, so I think I'll just leave this one for tomorrow. But like I said, tomorrow we're continuing on with the same exact thing. We're going to just do so many problems that by the end of class, you're going to, whether you like it or not, you're going to understand how to do it. So look forward to that tomorrow. And there are assignments on Khan Academy. They're exactly like the bell ringer. So they're easier than what we did in class today. It's just the writing a function. That's all we're doing. So that is going to be, it's already up. It's going to be due on Friday at midnight. So make sure you get started on that as soon as you can so that you don't forget and leave it until the last minute. And to answer a question in the chat, yes, I am posting this on YouTube today. So look out for that a little later if you want to review it. All right, guys. So see you all tomorrow for
Have
more
a nice
confusion.
day, Lopez. See you tomorrow.
See you tomorrow. Bye. Bye, Allison.